So we're getting to closer to the point of the whole thing, and that is the representations of series of functions by series, by power series. Okay, so and these are the two tests, as they out of many are especially applicable. And so the test itself is here, the ratio test. And we also did one application last time of how this test would be applicable or not to a power series. So we applied it once here at the top, upper half, to this particular power series, which happens to be, as to be known, to be the power series of the exponential function, which we got through Taylor approximation. So partial sums of these are the Taylor polynomials. Okay, so that's works out fine. And through differentiation, remember how we get partial sums. So we take our function Taylor polynomials at 0. Okay, we take as many derivatives as necessary at the 0, and then we have our Taylor polynomials. If we keep adding terms to Taylor polynomials, we end up with a Taylor series that is dependent on x. Okay, so at that point we would have been able to prove the convergence of that series based on the error estimate that we had. But we have now a more direct way to do it. As you can see, that worked out pretty easily. Just take the ratio of two consecutive elements, okay? And it doesn't really matter whether it's centered at 0 or not. And then power series, that's the nature of it. The powers right here, we saw how the powers under the ratio, two powers cancel out, and you're left with one power. You're left with one power, and that is why the rest of the ratio also cancels out nicely, because these are the factorials. And then it was very easy to evaluate the limit right here. Okay, so it turns out to be equal to 0, and that is I wrote here R is, what is R? R is that parameter, the limit of the ratios. The limit of the ratios, which I probably should mention a bit more here. It is that's not the full story. I'm saying that R is that limit of the ratios, okay, absolute values. But what I'm saying here is also is that it's possibly infinity. So so let me put it this way: a number or infinity, plus infinity. So that infinity is also a possibility. Okay, so 0 is possible, so it's from 0 to infinity, and infinity is a possibility. It's not what we're facing here, because the limit is actually hold on a second, what happened here? n plus 1 0, yeah. Right. Okay. So then the point being that verifying those two properties is applicable when with whether or not that the limit is infinite or not. So certainly you can say compare R, a number, to 1 to 1, and you have those two cases. But on the other hand, infinity is also here. So this is where infinity belongs, to case number 2. To case number 2, if the limit is infinite, then we have divergence. Okay, so and that's not what we're facing here. That's a good outcome here. We ended up with 0, so we have convergence. We have absolute convergence. Okay, but you can imagine that when this is not the case. So let's try to imagine that, or just have a series which is divergent. Is not, it's no trouble whatsoever to come up with a series that is divergent according to this test. So say 1 over n. So we can actually demonstrate that our the harmonic series is divergent. So an is equal to 1 over n. the ratio an plus 1 over an is equal to n plus 1 over n, and the limit is 1. Hold on a second, that is... actually, the limit equal to 1 is the exception. So as you can see, r equal to 1, the test fails. So that's not a good example. Let me pick something else. Okay, let's pick something extreme. Square root. So all power series, by the way, all the not power series, but power p series. So whatever power I add here, they all the test fails. I put p here. Okay, so then I have here the power of n plus 1 to power of p over np, and it doesn't matter what that p is. The limit is 1, so test fails. Test fails for all p series, unfortunately, but we already know the convergence of p series, so that's not a big loss. But you can certainly pick something else, a summation of say 1s. That's also not n's. Okay, so an is equal to n, then an plus 1. Hold on, where's my? That's not it. Okay, so I'm looking for example of divergence. x1. Okay, let's try this. We'll take the series x to the n, power series. Okay, power series x to the n, and we'll try to apply the same analysis as here. Okay, so it worked out for xn over n factorial, which happens to be the exponential function. Let's examine what happens with this series. The answer will depend on x, right? So an is equal to 1. X to the n. Okay, so an plus 1 over an is equal to xn plus 1 over xn, which gives me the absolute value of x. Okay, so as you can see, it does not depend on x, which means that the limit itself is x. So that is, I don't have to write limit here. This is my r. This is my r, and then if we just turn back to the original statement of the ratio test, then we have pretty much two cases. That number are less than 1 or larger than 1, and that gives me the different results. But that r is the absolute value of x. So as I said, the convergence of this series will be, unlike the last one, dependent on x. The last one meaning the exponential function. As you can see, no matter what x is, the convergence is to 0, and we have the limit is 0, and convergence is assured. Okay, but this one will depend on x. So we have by the ratio test, we have that absolute convergence when x is absolute value of x is less than 1, and we have divergence when x is larger than 1. Okay, so it is an interesting but typical situation is for what values of x we have convergence, and this is what we see. So yes and no and no. From -1 to 1 we have convergence, and outside we have no. The x equal to 1 is still equal to 1 is still to be established. Okay, so because the test fails. Okay, so it has to be looked at separately. Okay, so as I indicated, this is yes, and this is no. Considering that our polynomials are our power series are polynomials growing in degree, polynomials are defined everywhere, and they are continuous everywhere, and they seem to behave nicely. But as we have seen in the past, I think we've seen this picture previously of this particular series. I think so. Where is it? That's the one. Okay, so so as you can see, well, it's not obvious. It's still to be discussed, but actually, you can see the pattern that I just described. It is visible. It is visible what's happening to at the end of this interval, negative 1, 1. Let's take a look. So say, well, this is negative 1, 1, negative 1, 1. Okay, this is my interval, negative 1, 1. And so do you see what's happening at the edges, at the endpoints of this interval? So what's happening to our polynomials, the red ones, at 1 and negative 1? Well, let's do one at a time. So, so nothing interesting. Let's start with the second row because that's where things start to become visible. So around this point, what is happening to the red graphs? What's happening to the red graphs? You see the growth?
It seems to be forming, they're going to infinity, but it seems to be like pushing up a vertical asymptote.
Right. Well, but all of them taken together, because once again, these are polynomials. Polynomials do not have, each of them does not have a vertical asymptote. So it is only as a whole, and as a sequence of polynomials, we can see that indeed they together approaching that vertical asymptote. So that vertical asymptote is here somewhere, like this. And even though, let me, well, it actually looks quite visible. This is the one. Okay, so that's the one. As you can see, every time the red curve will cross it, because it is a polynomial. Polynomial's domain is everything, so it will cross it, but it crosses it closer and closer, sooner and sooner. And ultimately, at the limit, it will become vertical, and you end up with that green curve. So that's the idea. We're approximating the green curve with the red curves. The red curves are polynomials, and that's why they exhibit that behavior. And so they be on the right end. They're becoming steeper and steeper. But still crossing that vertical line. But if at the end, you may imagine that they will, what is at the end? It is a bit hard to imagine actually what happens in the reality, because there is no end as such. The function that always passes beyond, the graph always passes beyond 1. All of these red graphs are beyond and go to infinity beyond it. However, if you concentrate your attention on the interval between negative 1 and 1, then everything becomes clearer, because indeed you will see how, if we concentrate on the part of the graph that is to the left of 1, so like this, up to this point, okay, up to that point right here, and we ignore what's the rest, like this. Then you can see they're getting steeper and steeper and steeper, and becoming more and more, looking more like an asymptote. Okay, on the left, a similar thing happens. I guess slightly different. As you can see, if we take a look at it, it is, in a sense, it is worse, because you see why is it worse on the left? What's happening around this, at negative 1 over here?
It's giving vertical asymptote too, while it's supposed to be converging to negative infinity. With the green equation, it's supposed to be converging.
Well, we don't even go here. We don't look at these. We are staying with an interval between -1 and 1, and there is no a clear pattern to the left as to the right. To the right, they're getting steeper and steeper and steeper, and getting looking more like something with a vertical asymptote. It's not the case on the left. In fact, can you see how they oscillate between going up and going down, going up and going down, and so they're not getting steeper. They're not getting steeper, not in the same sense. If you just imagine that this green curve is being approximated better. This part over here is being approximated better and better by our red curves. So which is really hard to do when you have to go up and down, because it's going kind of up, following that green line, and then it goes. And then it remembers I'm a polynomial. I have to go either this way or that way, and then it oscillates depending on whether the degree is odd or even. And as you can see, the result is strange, because we know it's going to end. Where we're going to end up at -1. We're going to end up at what? At 1. At 1. So this is how high it is. This point is at 1. At 1, right? And beyond then, a behavior pretty much worst kind, and that is the one that oscillates. Changes between -1 and 1, positive and negative. So there is no pattern that we can catch on and try to understand. That's okay, because that's what our algebra told us. It told us that we only can speak of those series in meaningful fashion only on the interval -1, 1. Okay, so this is the only meaningful part. So this is meaningful, and these two are not meaningful. So we cannot speak of a series unless it has the sum, unless it converges. So if it does not converge, it does not exist as such. It's just a bunch of numbers. It's at best a sequence. So for these values of x and beyond -1 and 1, we cannot speak anything, even though there is certain degree of disappointment here, I suppose, because look at this green curve. There is whatsoever, this is the original curve right here, there is really nothing bad happening to the left. To the right, we can see over here we have a vertical asymptote, we have discontinuity, we have a break. So it's not surprised that there is nothing good is happening at that point at 1. But why the behavior so bad in here at this point? That is this point. Why? Look at the graph looks perfectly great. There is no break, no discontinuity, no weird behavior. It behaves just fine. But then we start approximating, and then turns out there is no convergence. No convergence. So this part of the graph is gone. Okay. As far as the approximation is concerned, Taylor polynomial, so Taylor series, won't give us any help with that part, even though there is nothing wrong with it whatsoever. And you can probably guess what's wrong with -1. What is so special about -1? Well, think about, you see the symmetry? Right? The bad point is 1. The center is 0. Okay, so the logic that we have discovered here is that interval has to have a center at the center of the meaningful interval has to have the center at the center of our approximation. So we were approximating at 0, and then we have to go equal distance to the left and to the right in order to have that meaningful approximation. And that because we cannot go beyond 1 to the right, that is why we cannot go beyond -1 to the left. If that makes any sense, and it is other than big reference to symmetry, you cannot really explain it why that should be this case and not some other case, why it behaves this way. So either we refer to the symmetry or we refer to the pretty much ratio test, which produces these results, right? So look at it, how it produces. Cannot be anything but symmetric, because no matter what the series is, we're going to do the theorem next. But other than that, we cannot see it cannot be anything but symmetric that way. The true answer, I think, lies in actually with complex numbers, as the best way to explain it. If these all numbers were not real but were rather complex, then instead of having an interval, we're going to have a circle, which makes kind of a slightly more sense to speak of things such as the radius of convergence. Okay, so but that just doesn't belong here, and so let's just state the theorem. The corollary from the ratio test applied, how it is applied to power series. Okay, so apply ratio test to power series. So how? So I have my series, say Cn x minus a to the nth power. A general power series, so we do not discuss its whatever that function they're supposed to represent, because we want to go back and forth from functions to their approximations or representations by power series and then back. So suppose we have a power series like this. This is just a sequence of numbers, and now if we apply the ratio test, we have an plus 1. Well, an is this term, Cn x minus a to the n. The only difference is it is dependent on x. Okay, so this is my term. Then the ratio test applies by taking the ratio an plus 1 over an, absolute value. So it will be Cn plus 1 x minus a n plus 1 over Cn x minus a n. Okay, so these are the ratios, the absolute values. We got to take the limit of this to apply the ratio test, but we simplify first, and we have simply this Cn plus 1 over Cn absolute value, and what I'm left with, just like in the last example, we cancel out these terms, the power terms. It will be x minus a absolute value. Okay, so then the thing that we have to, well, then this is a constant multiple. So which means that it will not make any difference as far as convergence is concerned unless it is equal to 0. So if x equal to a, obviously x equal to a, we have convergence. So that's not interesting. From the very beginning, we can say if I plug in x equal a, I'll have a bunch of zeros, so it converges. So if it's not, then it doesn't matter what it is, as long as the limit of what's left exists. So we have to look at this. So, and ask ourselves, does it converge? So the coefficients of our series, the question is, does the sequence converge? And that is what our theorem will tell us. Okay, so let me state the theorem. Okay. Here somewhere. Okay, so corollary. So suppose we have a power Cn rather. A is a real number, so that's going to be the center. Cn is a sequence, and then we assume that there's a limit. Cn, absolute value, rather the limit. I'm sorry, the limit Cn over Cn plus 1, Cn plus 1 over Cn, as what we're looking at right now, and suppose it is equal to r. So suppose this, which once again could be infinity, a number or infinity, and so infinity is a bad one, and then we have the same property for the convergence. So okay, so so remember that I guess I jumped a little bit ahead of myself. We have to look at, it's not an R but rather some different number. How about I call it no, it's how about I call it R capital? Okay, so because it's not the same as the R in the no, it is the same. Okay, let's make it R, little R. Okay, so we have to look at the limit of our sequence of ratios like this. So suppose we have a convergence of this thing times R x minus A. It is R capital after all. Okay, so if that limit exists according to the assumption of the corollary, that limit of ratios exists and is equal to R capital, then x minus A is simply multiple by constant multiple rule. We have this, and then we're supposed to check out whether this number, which is R, referred to in the ratio test, whether or not it is less than 1. Okay, so once again, we started with ratios of our power series. The power parts of each term cancels out, but not entirely. We're left with one x minus A term. Okay, and then suppose the limit of those ratios, Cn over Cn plus 1 over Cn, is R capital. Okay, so then the limit we're left with is the one on the right, so R multiplied by x minus 1 absolute value, and then that is our R. That is our R in the ratio test. So once again, this is the ratio test, and this is the R we're talking about. Okay, and then once again, whenever that number R lowercase is less than 1, we have convergence, and otherwise we have divergence. So, and that is what we would like to conclude. But what is important to point out is what is the region of convergence. So if we want to collect all the x's together in the inside of the all x's for which the series converges together, then we're going to end up with a series with an interval. Shit. Where's my formula? Not this one. Come on. Where is it? Oh, here it is. Okay. Okay. So then this is what we're looking at. Okay. So once again, we're looking for all the x's for which there is convergence, and they have to satisfy this inequality. Okay. That's all there is. That's all there is. It has to satisfy this inequality. If it does, then that limit according to the ratio test is less than 1. We have convergence for every x. If it is larger than 1, we have divergence for those values of x. Okay, so so then that's the conclusion of our theorem. The power series sum Cn in x minus A to the nth power converges absolutely. And now we're using slightly different language. Rather than saying it is converges for each x that satisfies the inequality, instead I'll say that it converges on a certain set. Okay, and that set is x minus, what is it? A minus 1 over r, A plus 1 over r, R capital. Okay? Okay, so that interval is the solution to this inequality. So x minus A, the distance from x minus A is, I could rewrite it if it's more convenient, x minus a is less than 1 over r capital. Okay, so that's the same thing, and that's what the inequality means, that the distance from x to a is less than 1 over r uppercase. Okay, so and that creates an interval, an open interval from 1 minus 1 over r to a plus 1 over r. So it is an interval, and on each point within that interval, it is convergent. Okay. The only thing, if we want to be careful, we want to say that this is true when r is finite. Okay. So once again, two cases for that limit. One is infinite, the other one finite. And when it is finite, then well, actually, that's not what I was worrying about. R not equal to 0. So we do not want to divide by 0, so r not equal to 0, then this is the interval. When r is equal to 0, then the answer is, as you can guess, what's the answer? Well, look at the inequality. What if r capital, our limit, is equal to 0? What does our, if you look at that inequality at the top right, and r uppercase is 0, then what do we get? If this is 0, then what? Well, 0 multiplied by x minus a, absolute value, what does it give me? Zero multiplied by anything gives us what? It gives me 0. So then the inequality that I'm supposed to verify is this expression less than 1? It is, because it's 0. So 0, definitely less than 1. So the inequality is satisfied, which means that we have convergence no matter what x is. Right? So the inequality, that inequality may or may not be satisfied depending on the value of x. That's the original idea. But sometimes it does not. That is when the limit is that r uppercase is 0, because the whole thing turns into 0. The limit is 0, and 0 is less than 1, so it's always satisfied. Okay, so that's the extreme case. The limit is equal to 0, and then we then have then the answer is it converges on what? Every x. From negative infinity to positive infinity, just like that example from last time, the exponential function has the limit equal to 0 of those terms that are uppercase, and converges for every value of x. So this is called the interval of convergence. And 1 over r is the radius of convergence. Okay, so that's the to classify the power series, we're going to use this language. And so the two examples that we had was the interval of convergence was negative infinity for the power series, and for the exponential function, and the other function was from negative 1 to 1. Okay. Including the endpoints, if you include the endpoints. Okay. So what we have here is there are more cases to worry about. So these are two cases. Two cases. There is the third case is r is equal to 0. I'm sorry, r is equal to infinity. Then it converges it converges for a single value. It converges for a single value of x. So when the limit of R is infinite, there cannot be any convergence because the limit is infinite, and according to the ratio test, the limit is when it is larger than 1, including infinity, then we have divergence. The only exception is, once again, if we plug in x equal a, we still will have convergence. So that's the extreme case, which we have seen. And we have, as you can see, we have, that's the case number 3. So I have to add here and diverges outside of this interval. Okay, meaning we're still skipping the endpoint. So we're careful here, even though it doesn't really make a big difference. We have the whole interval of convergence, and the 2 points out of infinity, many points on the interval, there are 2 endpoints, and they are not have not been taken care of by the theorem. So, well, they have to be verified separately. So it is possible that either both or one of the 2 endpoints might be convergent or divergent. Okay, so so the example that we have seen, and probably time to verify it, is the once again this series. Okay, as you can see, the interval is between -1 and 1, but the question remains: is -1 and 0 included? So do we include -1 and 1? Okay, so let's take a look. Let's take a look at the picture. So, do we include 1? So the question is, do our polynomials converge if we slice? Remember how we do it. If we slice the whole picture and we cut out of that picture nothing but that vertical line, dashed line. If we take only only that out of the whole picture, then will be their convergence. So if you all you have to do is to look at these values. This is what I'm talking about. This, and then that, and this, and that. You see what's happening? What's happening? It is where our graph of our polynomial, the red one, crosses that vertical asymptote, and it crosses it higher and higher and higher. So the limit is what? The limit is infinite, and which is what we want, because that's the way our function behaves, the green one. But it means that there is no convergence, or can be convergence, because the function itself is undefined at 0, so we cannot or should not expect convergence there. So the answer is no. To this one, the answer is no, because the function that based on that illustration, it appears that the function we know that the function is undefined at 1. So we are hoping that there is no convergence. Otherwise, it converges somewhere to a place that is not right, because the place that is right is infinity. So there isn't. So the answer is no. What about -1? The blue one. Well, the blue, what is happening to the red curves right above the blue point? So the points that we care about are these. This one and that one. Look, they don't even see to, there seems to be not much is happening to them, is there? So I pick the point right above the blue one on the red graph. So if you can conclude anything from that picture. What's happening to the black points? You probably need more points to be convincing to see how the long-term pattern, but you can probably guess. If I put more points here, the red one here, and then over here, and then they seem to be not going anywhere, right? So these are the points above the blue one, above -1, so that's all -1, and they certainly their behavior is different from x equal 1, where it goes to infinity. Here it is not going to infinity, so it is at least reasonable to guess that there might be conversions there. And indeed the answer is yes, and we're gonna verify that. How? We just plug in. So x equal 1 and x equal -1 and 1, and we plug it in and see what's going to happen. So okay, well, summation of -1 to the n, well, it does not converge. Summation of 1, that 1's to the nth power, it is 1 plus 1 plus 1, and it is equal to infinity, so it diverges. But the other one also diverges. Why is it diverges? I mean, it is divergent. Okay, yeah, so this one is 1 minus 1 plus 1 minus 1. So it is a different one, but it is it also diverges just in a different manner. So this one diverges to infinity, and this one just diverges. Okay, so so it does not go into infinity. It appears to be. What the hell is possible? It appears to be appears to oscillate between -1 and 1. Right? I'm sorry, between between -1 and 0. So it will be, if you look at the partial sums, it will be 1, 0, 1, 0, 1, 0, and so on. So it is certainly divergent, but it's not going to infinity. I guess that's what we're seeing here. Yeah. If you look carefully, I guess at the same, if you try to use the same, the scaling is messed up here, but if you look at the intersection, you can see, yeah, you can already see a bunch of zeros. This is 1, 0. This is the other 0. This one is 0 if you look carefully, and this one is 0, and that one is 0 too. Okay, so the red polynomial crosses the x-axis at -1. Okay, and but the other one is supposed to be 1, so this is 1, and over here that is 1, so this is 1, and this is 0, 0, 1, and so it oscillates between -1 and 1, and so we have divergence again, even though there is no running away. So then the interval of convergence is -1, I'm sorry, -1, 1. Excluding the endpoints. Okay. Okay, so that is our theorem once again. So the method is more or less explained here. So you got to start with that limit, and it is up to you. I mean, this derivation is fairly quick. So if you just remember the ratio test, it will be sufficient for you to derive it very quickly. The logic is the same, so just looking at what that limit is, and then based on that you will every time end up with that is something you should remember, for what values of x it converges, and it always, every single time, it is an interval. It is an interval which may be infinite both way infinite, so it cannot be like from 1 to infinity or nothing like that. So either it is all symmetric. It is symmetric around A, so center here, center at x equal A. Okay, it's centered around A, and then you make a step to the left and to the right of the same length, which could be infinite. Then you have the whole thing that's at the bottom. Or it is not infinite, then you have an interval centered at A, And finally, the last part of analysis is what we just carried out. Look at the endpoints. Look at the endpoints of the interval. So as you can see, we only say what's happening inside. That's what's happening inside of the interval. And then we know that it is diverges outside of that interval. That's all. So the endpoints are not covered. So the endpoints aren't covered, and the reason is because the r equal to 1 is when your ratio test fails. Okay, so you have to consider them separately, invoking things other than ratio tests or power series or anything like that. So you will be invoking p-series, geometric series, or p-series, geometric series, one of those two. Okay, so we'll do a little bit of that next time.